Hello everyone, and welcome to Applied Simulation Day. My name is Eric Miller, and I'll be conducting the first of the 3 sessions that are scheduled for today. They'll be kind of focusing on the 3 primary tools that Autodesk provides for doing analysis on your models. Obviously there's a few different levels of that, so the one I'm working with is today will be Inventor Simulation, which is the built-in tool that comes with Inventor Professional. So there are some really cool things you can do now. Obviously, with simulation built into our CAD tools, there's so much more than what we had 10, 15, 20 years ago to be able to find out what how our models are going to react prior to building an actual physical prototype, to try to understand how they're going to react to forces and the constraints that we're going to be applying to them. So within Inventor Simulation, there's some good tools for linear analysis. So we'll talk a little bit about today too on how to determine which tool or should be applicable to the situation that you've got, to the design that you're working with. So, I guess just to kind of name the 3 different tools you can see today as well, we've got, like I'll be showing you Inventor Simulation. Then there's also Nastran in CAD, which gives you some additional features and more capabilities, and then kind of the high level or the top product that Autodesk provides for analysis is Simulation Mechanical. So they all have some different capabilities. I guess the 3 tools have some of the same capabilities as well. So it just kind of depends on what type of analysis you're performing and what are the I guess the goals of your analysis. So that's what we'll be looking at today. And even to break that down a little bit further, since there is so many different things to talk about in an analysis situation, we're going to kind of focus more today on just preparing your model for the simulation, which is kind of the first phase. Obviously, even before that first phase, you want to kind of do some preliminary goals of your simulation. Try to maybe even do some free body diagrams, kind of by on a sketch or something like that, just to kind of understand what are you trying to get out of the simulation that you're doing. But once you get into the actual task within Inventor, one of the key things up front is to simplify your model, prepare it for the simulation. Before you even create a mesh, we want to understand, try to figure out the types of elements that we want to use, and then get rid of the stuff within your model that maybe you don't need. So we'll talk about that a little bit today. So let's go ahead and move in. I've got a couple slides here, and I will get into the live system here after a bit as well, and kind of go through the process of preparing your model for a simulation. And if we have time, I'll even try to just complete, follow through with, at least getting to the point of seeing some of the analysis results, analyzing that a little bit, depending on how much time we've got today. So. But just again, so what is FEA? Obviously that stands for Finite Element Analysis, but what are we looking to get out of it? And really it's just another tool to help us better understand our product and make informed engineering decisions. So before we had some of these capabilities, you'd come up with a design, you'd maybe calculate out some of the reactions and how you or some of the stresses and the strains and stuff like that, by hand. Obviously it's been a while since maybe we had to do that, but it's always still good to kind of keep those things in mind. Don't just depend on your computer to do everything for you. So definitely a good idea to still do some of those calculations and free body diagrams and stuff like that by hand, just so you kind of have a good idea of what you're looking to expect. So again, with FEA, the further upstream we can gain knowledge about our product or our systems, the more valuable this information becomes. The further a design flaw goes down the line, even all the way to manufacturing, obviously if we find that flaw down the road when it's already in our customer's hands, I guess the dollar amount, the time it takes to resolve those issues and to make our customers happy again, obviously there's a huge cost and time commitment and possibly some really poor, I guess, customer feedback and just satisfaction, those types of things. We definitely want to figure out our design issues as early as possible. So that's what these tools really help us do. All right, so one of the first things we have to determine before we start jumping into an analysis is, what type of analysis are we looking at here? So, and for Inventor Professional, for Inventor Simulation, it has to be a linear analysis. So how do we determine what's linear and what's not? Well, there are a couple things to look at. So in order for it to be a linear analysis, we want the stress-strain curve to kind of look like it does over on the right, the little image on the right, where you've got typically a linear curve up until the point where it starts to reach its, past its yield strength. So then you start to deform the material, and eventually you reach a fracture stress where it breaks. So, I mean, if we're working within the linear part of that, kind of on the left side of that curve, that means we can, expect whatever stress or whatever forces we apply to our material or to our design. We're assuming that after that force is taken off, if there is any deflection, it's going to go back to its original state, and there's no plastic deformation or anything like that. So that's kind of what we're looking for in a linear analysis. But some of the other things to think about here are as far as deflection, rotation, stuff like that. It's got to be pretty minimal in order for it to stay within that linear realm. Also, we have to make sure there's no strain stiffening. So that kind of changes the behavior of our materials if it does get to a stiffening point. The elements. So is there any frictional contact that we're taking into account? If that's the case, then it tends to become nonlinear. And then also the materials that we're using. So if it's steel, if it's aluminum, stuff like that, where it's got a pretty well-defined stress-strain curve that does have the linear portion, where we're not having any permanent deformations, then we can assume that it's linear as well. However, once you get into plastics, some composites, some of those other types of materials, then that also takes it into the nonlinear. All right, so that's just kind of a little example of some of the things that would allow it to be on the linear side. So here's an example of what a nonlinear analysis might look like, or things that move into that realm. If you look at the stress-strain curves over on the right, they've got pretty much there's no constant slope there. It's continually changing, so that tells us that it's more likely a different type of material, like a plastic or something like that. So, so again, kind of back to those same elements: geometric, element, and material. If there's large deflection, there is strain stiffening, then we know it's going to have. We aren't going to be able to perform that analysis within our Inventor simulation product. We might need to move to Nastran in CAD or go to Simulation Mechanical to be able to get a true understanding of how our part's going to react. Also, if there's friction, nonlinear formulations, and then obviously in the materials like we talked, the plastics and the hyperelastics, the hysteresis, some of those things, those types of materials are going to be push it into the nonlinear. So just a couple things to kind of keep in mind to determine, is it linear or is it nonlinear up front? Okay, now, so maybe we figured out if it's a linear thing and we think, okay, we can do this in an Inventor simulation. Maybe it's more of a simple issue, or even if it's fairly complex, you can still do, both static and dynamic types of analysis within Inventor Professional. So those, there's a lot of capabilities there. But even before we start diving into it, maybe we've got our model designed. Don't just jump into it and start adding your forces and constraints and whatever it might be. It definitely take a few minutes if possible to kind of plan out. Okay, what am I looking to find here? What are my goals of this analysis, and what type of analysis am I doing here? Is it buckling? Is it am I looking just for the stress involved there? We're looking for deflection. What are my goals of doing this analysis? Obviously we want to get some value out of that. So we also want to qualify the inputs. So where are my forces located? What are the values? What is the overall loading on my design? What are the restraints? What are the environmental conditions? What's the temperature? Are we, temperature can play a big part in this too. If it's in a cold climate versus warm climate, those types of things. So definitely try to understand those criteria here before we start diving into, applying those things in our model. We want to make sure we define and document our material properties. So we've seen it many times on a drawing where, somebody doesn't think to design out this, really nice elaborate part or whatever, but they forget to apply just the simple things like making sure your density is correct and the material properties are correct. So that plays a big part, obviously, in an analysis to make sure the right material density, yield strength, tensile strength, all that stuff is accurate. So keep those in mind. Make sure they're input into your model. Define prediction theories. So we want to try to take our best stab at figuring out what this design is going to do. Where do we expect it to fail? Where do we think the pinch points are? Or if there's sharp corners where the stresses might be higher? Where's the loading where's the impact going to be from our load? So definitely try to understand, and predict what the design is, how it's going to react to this analysis. And then, like to show here down at the bottom, create a free body diagram. Just try to, take your, hopefully you've had some background in analysis. You probably had to do, if you've done any kind of simulations, whether it be in school or throughout some of your design projects that you've done. Most likely you've done a free body diagram, maybe create the Moore circle, that kind of stuff, and just kind of lay it out on a sheet of paper to kind of help understand what's happening when we get into the actual analysis. Okay, so those are some pre-computer tasks that are always good to do prior to actually getting into the Inventor analysis. All right, so here's kind of a fairly simplified, but really these are the 4 steps, or obviously you might, in other literature, there's probably a lot of different, amount of steps anyway that somebody might consider in a stress analysis workflow. But this was taken from the Up and Ready books created by Wasim Yunus, and so within his information and materials regarding Inventor simulation, these are the 4 steps that we kind of break it down into. So idealization is the simplifying of the geometry and setting up the analysis. Then step 2 is the boundary condition. So applying those constraints, applying the loads, making sure that the model is locked down, and if there is any, and that's typically in a static or dynamic, I guess, analysis, where is there going to be any motion in that kind of stuff. Once those are step 1 and 2 are finished, then we get into actually running the simulation. So we need to create the mesh, right? Determine what type of elements that are used, run the simulation after that, and then analyze it. Does it seem to be converging? If we take a look at the results, are the stresses where we thought they should be? The values of the stress, are we past the yield strength? Those types of things. So I definitely want to take a closer look at that. And then step 4 is to optimize this. So change our geometry, figure out, and then step 3, I guess, too, if we refine our mesh and rerun the analysis, are the results the same? So, or do they change drastically? So that would, if they're changing quite a bit, that means it's not really converging, and maybe there's something else going on there with the analysis. So kind of keep an eye on that. But step 4 is really to optimize it. So if we are past the yield strength, what do we need to do to make sure we stay within the linear portion of that curve, where the slope is this constant? So what can we add? Do we need to strengthen our part? Do we need to remove some of the holes, or whatever it is that's where our stress is highest? Do we need to consider maybe you have to have another factor of safety factor, take that up another level from say 2 to 3 or 4, and make sure that we're not going to, our design isn't going to fail, is really kind of what we're trying to get to here. All right, so once you optimize, we can rerun the analysis several times and then compare the results and make sure that our final design is good to go. All right, so the part we're going to focus on here is the idealization. So that's more of the geometry simplification and preparing our model for the analysis. So there's kind of a list of questions here that we kind of came up with on, before just starting to apply your constraints and loads. Let's figure out what can we do to prepare our model here and make it, have the best chance of getting good results. Okay, so first of all, what assumptions can be made here? Can we remove some parts? Can we, that aren't really in the, I guess, the line of of fire as far as where the forces are going to be highest and how it flows through your model, where the stresses are going to be the highest. And maybe there's some extra material or extra pieces or in an assembly, I guess, scenario, are there anything in there that doesn't actually, wouldn't be required? Can we simplify the design? Maybe there's too complex. Can we, maybe create a shrink wrap of the model in certain cases? And that kind of goes into the step 2 there. What simplifications can we make to our model? So, in a part environment, we can defeature the part by taking off, holes, rounds, different things like that if they're kind of not, in a critical area. We can use shrink wraps to kind of reduce the overall size of the model, and shrink wrap substitutes. We can use levels of detail to remove things within an assembly. We can also use direct modeling to kind of, maybe change shape in certain areas to take away some of the, extra mesh pieces that would be required, as long as we can, assume that they're not going to be affecting the high stress and strain areas of our analysis. All right, number 3, is there symmetry involved? A lot of times our models do have symmetry, whether it's, just kind of left side, right side, or top bottom, or even, in a circular, type of part where there's, it's got symmetry in more of a circular fashion. A lot of times we can cut that down and only perform the analysis in a certain section of it. That's going to require much less mesh elements, and speed up our analysis. Sometimes these things can run for quite a while, so any time you can save there can definitely be beneficial. All right, can non-structural components be excluded? So I kind of mentioned a little bit earlier on the assumptions, but if it's not really kind of in the, I guess, the line or the train of where the how the stress would react through your model and kind of flow through, I guess, as far as the, where the force is going to react and the reaction, I guess, reaction points within your model. If it's outside of that, if it's a, bolts or washers or nuts or something like that that aren't required in there, we can sometimes remove those and not have any ill effect on our design. Okay, number 5 here, can the loads be correctly applied? So a lot of times we see that with, some of the forces. Obviously, if it's just a point force or pressure, throughout your, on a surface of your model, those are fairly easy to apply, and we can expect them to, to react pretty, or at least have a good prediction of what the reaction might be. However, sometimes if, we see a lot of times like in a torque loading or maybe there's just in a different, kind of in an odd direction potentially, we have to, question whether or not that load is being applied correctly. So sometimes a dummy component can be added to try to facilitate that. So that's something you have to kind of think about within your model. If you've got some complex geometries in there and maybe where the load is applied is in a different direction, or it's rotational or whatever it might be, try to think, would it help to put in, a dummy component, simplify my model, but still apply those forces through something else that we can add to that to be able to kind of verify or to make our results a little more accurate. Will removing welds, adhesives, whatever other types of bonding you've added to your models, if we take that out, is that going to affect our results? A lot of times, welds can be left in, and as long as they've been applied correctly, it can really change how forces and stresses kind of react in a model. Obviously, if there's fillets and rounds and stuff like that, kind of same thing. Sometimes if you have a sharp corner, that's where your stress might be. So you might need to leave that round in to make sure that the stress is when you're going through the actual analysis, is more realistic and more lifelike than if you take some of that stuff out. So some things to think about there when you're going through. And so question number 7 there, is the correct material applied? So that's obviously going to bring in the right properties, like I mentioned earlier, the density, the yield strength, and stuff like that. So definitely make sure the correct material is applied. And also, if it's multiple materials within an assembly, don't just apply the same one to all of them. Some of those hardware pieces, your steel, it might vary from piece to piece. So definitely keep that in mind and make sure that, for each specific part, the right material is applied. Should thin or solid elements be used? So by default it's typically a solid element, but and that'll just kind of, you know, we're talking about the mesh. When you go to apply a mesh, what type of element is applied, and a lot of times it's solid elements, depending on how low you go with your mesh or how refined you get it. You know, there's going to be a lot more pieces there. With a thin element, if you're working in, say, like a sheet metal environment, sometimes thin elements can get you just as good a results or maybe even better, but you have a lot less data there because it's a lot, you know, fewer elements if you're looking at you know, using thin versus solid. So that kind of just depends on the design that you've got, if there's some sheet metal in there, but that you can use thin. Also, there's beam elements, so number 9 here. Can we allow that? Is it acceptable? A lot of times, if you're using the frame generator within Inventor, those can automatically be converted to a beam element instead of having to go through and kind of define it yourself, and content center components as well. So if beam elements are acceptable, if you've got, you know, a lot of similar geometry and, you know, constant cross-section type of stuff, those beam elements are fairly handy and can simplify it pretty good. Should solid bodies be used? So in an assembly environment, or even in a, you know, part scenario where you've got multiple parts, solid bodies can kind of simplify that a little bit too, rather than keeping them all as their own sub-assemblies and assemblies. So just a matter of kind of simplifying that prior to going into an analysis. All right. So those are just some of the questions to kind of think about. I mean, there's a lot of other stuff too, depending on your design, how complex it is, you know, to think, you know, how do we, what things can we do to simplify it before we start creating our analysis. Okay, so let's jump into an actual scenario here. So and utilize some of those concepts in order to simplify and prepare our model for the analysis. All right, so in this case, we've got, this is an airbag lifting jig, and you can see the suspension piece is down below here. But what we're trying to analyze is this designed for our lifting jig? So this is going to be the lift point up on top here, and then over on the sides you can see the weight is all basically going down here through this angle channel. Okay, so we got that side and then this side. That's really the only place, you know, this is a piece of the suspension there. So we want to know that how is the force going to transfer through here? Where is my main stress? And obviously, if you're looking at this, you know, you can kind of start determine, or kind of try to predict where my main stresses are going to be. You know, if this, you know, is this channel too narrow potentially? If you think about how that's going to, you know, put a force on that around the bolts potentially, or even up on top, you know, do we need to make this piece a little bit thicker to make sure that has enough strength? You know, are the welds there placed properly, and is there enough there? Obviously, down in the bottom too, we've got, you know, fairly thick angle piece here, but you know, you've got a direct, you know, a 90-degree angle on that, so a lot of the force is going to be kind of going through that angle up into this piece. So is that where a lot of bending and potential deflection is going to happen? So I want to try to, you know, think about that a little bit, you know, and then where our joint right here, you know, what's that going to look like? And obviously, you can see there's going to be some compression here in the center. So we've got a bolt that's kind of holding this sleeve, or I guess the channel here, square channel, or I guess it's maybe rectangular tube, you know, into the other sleeve. So how is that going to react? Is 2 bolts, you know, going to be enough to hold that? Is there going to be stresses in there? So those are just some, you know, just kind of a quick just visual analysis, or, you know, kind of making your own kind of predictions in your mind. Obviously, it'd be good, like I mentioned, to do a free body diagram from this, you know, kind of lay it out, map it out where we think our force is going to be, and those kind of things. But for the sake of time, we're going to jump right into, you know, some of the model preparation techniques here. All right. So first thing we can take a look at is our, you know, can we get rid of some of the rounds? You know, whenever you have rounds in a model like this, it creates more mesh elements. So if we can get rid of the rounds, a lot of times it'll you know, improve that as far as the overall size of your mesh. But you know, obviously you want to be sure that there's not any stress risers there. And in this case, this is all basically going, you know, it's going to be compressing, you know, into each other, so, or compressing into each other. So the rounds really, at least we can maybe assume that they're probably not going to have a lot of effect because the force is going, you know, towards the center of the model. So let's go ahead and do that first before we even get into the analysis environment, let's go ahead and jump into the outer clamp. So here's my outer clamp subassembly, or sorry, yeah, outer clamp. And let's get into this O channel. Just going to double click on that to select it. And we're just going to, you can see there's a fillet here on the inside corners. Let's just take that out to try to reduce. We're just going to suppress that feature. Okay. And you can see one back to a square. Let's do the same thing on the other inner clamp. And we'll make sure we pick, let's select that, and now let's pick the, where's my inner clamp? There's my I channel there. Let's switch over to the model view. And so here's another fillet on the inside of that one, and then the outer fillet too. Let's just remove or suppress both of those. We're not really, oh, we gotta double click on that activate that part, and let's suppress it. I want to just delete them. We're just suppressing it for now so it isn't taken into account. Okay, so that's suppressing a couple features. Here, let's say we want to, we think this hole too isn't going to be critical since the force is kind of, again, it's compressing there through the channel, so we're not really worried about that being strong enough. We're more worried about some other pieces of this being, strong enough. These channels are pretty pretty large. We're pretty comfortable with that, and maybe we've seen some different designs similar to this in the past, so we feel like we can remove that. So if I go back to this other channel, let's go ahead and get rid of the hole there. Again, that'll remove some of the need for multiple elements. Let's see how it's outer clamp. Double click on the O channel again. Let's see, where's there's the extrusion. Let's just take that and suppress that as well. Get rid of that hole. Okay. Let's go back to activate the entire model. And now that we've gotten rid of some of those features, so like holes, chamfers, rounds, or whatever it might be, something to look at for that as far as simplifying your model. So now let's jump into the, we talk about removing some of the non-structured components would be kind of maybe one of the next things to look at. But let's do that within the actual analysis environment. So I'm going to go up here to environments. Let's go over here to my stress analysis. Take us into the simulation part of Inventor. And we'll just go ahead and create a study. So it's kind of the first part of it. Now one of the things when you're creating the study as well is to come in and, so a lot of these there might be some minor gaps. So if we want to consider, a contact to be made as you're creating these contacts, so eventually we're going to have to take a look at how these parts are all contacting each other. Do they need to be a bonded contact? Is there sliding? Is there freedom? What degrees of freedom are left there? So in order to work with contacts, sometimes it's nice to work with this tolerance here. Right now it's set to point. We're going to bump it up to 0.3 in order to generate more automatic contacts when we go to do that. And you see the type here is set to bonded. We can always go in and change those later too. So let's just go ahead and leave that as it is. We can change the name of my analysis here too. Let's just go now. Analysis Wednesday. Hit OK on that. So now that takes us into the analysis environment. Notice a lot of my other tools now within the analysis tab are now active. So now we've got our constraints over here. We can assign our materials. We can put in our forces, pressures, other loads down here below. If you keep sliding over to the right, we've got the mesh. That's when we go to create our mesh, generate the mesh, and then eventually once we complete it, we'll run the simulation, and then we can kind of go through our different results. So there's also some other stress analysis settings, and then kind of, I don't know if you can see it all, but on the far right, once you're completed with it, you can finish the analysis. But all right, so one of the first things we want to do is exclude the components that we don't think are required in here. And actually, since we're going to apply our own forces down here on this angle, we can get rid of the entire piece that we're actually lifting. So let's expand that out, and we'll just select the secondary suspension here, right-click on that, and then just do exclude from study. Okay, so that kind of puts a little indicator next to it within the model tree, but it also kind of grays it out, or I guess makes it transparent a little bit there. So let's continue on with some of the other ones, like for instance this handle. We know that this is just on there to move this thing around. We're not worried about that being stressed. So if we go to the inner clamp, let's grab the handle, exclude that from the study. So again, we're just kind of simplifying it, taking out the non-structural components here. Let's go ahead and take, so in this case, we're going to create a bonded contact here between these two channels, so we don't really need, and that's we're making an assumption there, obviously, that this isn't where our high stress is going to be. We're thinking we got plenty of strength within these two channels. So let's go ahead and take out these two bolts just to kind of, again, reduce the overall number of parts required in here. So let's go down, let's see that piece, and the boss, we're going to take those and do exclude from study. And I think, is there another piece? No, that's a different one. So those are the two we can remove there. Let's see, what else here? I think maybe that's good for now. We've got the stresses, we're going to be pulling from the top, and then we've got the force in the bottom. So we've got to think it's going to transfer through a lot of these other connection points. So I don't think we want to remove too much more. Well, I guess I take that back. I think this washer, obviously all that's doing there is holding, in the nut, we're keeping that within, obviously connecting the bolt to it so it doesn't fall out. But as far as the force goes and the stress, we're not really concerned about the washer and the bolt here. So let's grab those and exclude from study. Okay, we'll do the same thing. We can just right click on that too. I can find it in the, obviously over in the model tree, but sometimes it's easier to do it here. Right click, exclude from study, kind of graze those out, and same thing up on top. Click on that, exclude from study. Obviously the bolt we need to keep in there because these connection points, they're this hinge, basically the bolt's going through that, so that's going to take some of that shear force through it. Okay. All right, so let's say that's about as much simplification as we can do there. So now we're really our model, and I guess just another thing, maybe you want to get rid of the way the visibility here, so we don't have to see that if we're going to apply forces here. It's kind of in the way right there, so we can do that through our stress analysis settings. So if we click on the stress analysis settings down here in the bottom, excluded components display as, and right now there is transparent. Let's just click the invisible option there and then hit OK. So just to kind of, obviously if you hover over it, they're still there, but now we're down to, this is what we actually want to work with. So now our model is ready to start adding the the constraints, the loads, eventually mesh, and we might need to simplify this a little bit more as far as, we look at the contacts in here, but I guess not really simplification, it's just making sure we've got the right constraints in place. All right, so we'll come back to that if we get some time here towards the end and complete that one. I do want to look at one other, when we're talking about simplifying a model, here we've got some symmetry, obviously in a circular fashion. So this is just a regular fan, kind of an impeller that we want to do analysis on. So how would we simplify this? Well, first you got to kind of figure out maybe how many there are and divide that by the overall angle, or what each piece would be. So if we want to just kind of do an analysis, if it's going to be symmetric, we can kind of cut out the rest of the stuff using the split tool within Inventor. So just to kind of show how to do that, if you've got model symmetry, to remove the overall number of mesh elements, let's cut out everything except for one basically core piece of the fan. Okay, so one fin. All right, so we could do that by, let's go get our model here lined up, and you can see right there, it's what we want to do is basically cut out and just take a little piece here over to the right, so just this fin. Okay, so we obviously want to make sure it's symmetric with the rest of our geometry. So you might need to make a couple calculations, but what I'm going to do here is just start my sketch to be able to split that. We'll put our sketch just on the flat surface there, and I guess maybe wireframe wouldn't be a bad idea here either on your view capabilities, just to be able to see that. Right now it's not realistic. Let's go to wireframe. That way we can see, make sure we cut out what we want to. All right, and actually, what if I don't want to rotate that? Well, let's go ahead and create it the initial way we were talking here. I think if I cut it and then maybe just, you wouldn't have to just go straight up. Obviously that would cut this fin. Maybe I'll go up and then kind of angle over with this cut. All right, so if we go back, we're in our sketch environment still here. Let's go to the sketch. We'll just start a line. We'll start at the center here, go up a certain amount, and then I'm just going to come over to kind of cut that piece off. And let's go out at an angle here, an angle out there to cut that off. So that's really kind of the chunk we want to take. So let's kind of drop in some dimensions here. We'll make this 200. This one 200. So let's see, I want to make sure that comes out at. I want to make sure that dimension was along the length. So as you're creating dimensions, and obviously if you've used Inventor, you know that if you hover over, when you click to create the dimension, then hover over the line or get real close to it, a symbol will pop up that lets you kind of create that dimension, that one right there, that you're going to create it along the length of your line. Okay, and let's drop in a couple more dimensions. This we want to be 36, and this one is going to be 101, and same with this one, 101. Okay, so obviously we'd want to verify that that's getting an exact piece that's symmetric all the way around. But you can kind of tell here if you look at the distance between these, I think we're doing pretty good. So let's go ahead and just hit finish on the sketch, and let's go back to the shaded view for this. Let's go view, shaded view, and now we're going to take that and with our model. Let's go back to the 3D model portion. We want to do a split. So here's the split tool. We want to split the entire solid. That's the second option here. And now what do we want to split with? We're going to use the sketch that we just created. And right now it's kind of pointing to the inside to trim that. Let's flip it to the outside and then hit apply to trim off the outside. And now we're down to just the part of the model that we want. Now, obviously, in this case, if you've got some type of drive shaft in the middle, maybe the force is going to be applied, to this. So we put a rotational force in there, and then we could, set up some of the other constraints here on the other surfaces in order to complete an analysis there. But again, I think for the sake of time here, let's jump back to the other one. So this was just an exercise in simplifying my model where there is some symmetry in order to then, now basically we'd go into our simulation environment, start the stress analysis, start another study, create a study, add our constraints and loads, and again, that's kind of the next phases of the analysis workflow. All right, so just to kind of follow through, I know kind of the fun part sometimes is actually seeing some results. So let's go ahead and just finish up this one, and we'll kind of see what we get on it. So first of all, let's do my fixed constraint. And I'm going to pick this inside surface. So that's really where my low, I'm going to put a hook through that or whatever it is. So that's going to stay fixed, and then I'm going to apply the force down here to the bottom pieces of that. So we'll go hit apply, cancel that. Now let's put a force down here on these bottom two surfaces. Now obviously we're making some assumptions there too, because remember how that the suspension probably didn't hit all the way through on this force. So we're saying that we're applying the force to the entire surface. We may need to create some splits on that surface just so the force is applied properly and not to the entire flat surface there. So, but we're going to assume that this is going to be okay. Let's just go 390 newtons there, apply that. And now let's go through and kind of check some of our contacts. Remember well actually we have to first create contacts. Let's go ahead and use the automatic first. That's going to try to find all these contacts within that tolerance and apply. Remember the default was to apply a bonded contact to them. Okay, so I went through and did that. So there's going to be a contact now applied between these three features. Let's go ahead and start reviewing some of those. If we take a look at, for instance, in here, that's going to should be a free contact because it's just a bolted connection. So let me see. Take a look at the bolt, and if we expand that out, bonded connections that were created. So we got a bond there, bond there, bond there. Now these are actually not in this case, in a bolted connection that's going to have movement and can rotate, we don't want a bonded connection. So first of all, it created a bonded connection between the surface, the bottom head surface of the bolt, and then kind of the bushing piece that's on that arm there. So we're going to just suppress that one. We don't actually want that to be bonded at all. That's going to rotate freely. There's not going to be any stress going through that. Now for some of these other ones, we actually want to convert these to, we're just going to hold Control, select all three. We're going to go edit the contact, and we're going to convert those from a bonded to sliding, no separation. So it'll allow them to rotate. Okay, we'll do the same thing with basically a lot of these other joints. All right, so let's pick this bolt, go in and expand those out. Again, we're going to suppress that contact, grab these three, and convert those to sliding and no separation. All right, let's take a look at the bottom piece here too. Let's grab that bolt. And so this, that outside surface we want to be, let's just suppress that one. We don't need that. And these other three, those are all going to be sliding no contact, or sliding no separation, sorry. Select that one. Let's go back to the other side here. I'll just pick this bolt again to get it in my model tree, slide those down. Okay, this one we're going to suppress. And then the other bolt connections that are all kind of going through there, we're going to make those sliding no separation. Okay, now there's just a couple left here that we have to look at. First of all, I guess there's no contact between these two right now, so let's go ahead and put a manual contact in there. And it'll be a bonded connection. We're going to go between this surface and that surface, just so you know we're assuming that they're going to be kind of bonded together. Obviously, we took out the bolts, so they are going to be. It's a little bit different than the actual analysis, but again, we're assuming that this isn't where our stress is going to be highest. So we're just going to make those that they're not going to move basically by putting in that bonded connection. All right, so that's a manual constraint contact that we can create there. Now I think there are a couple more though on the bottom because some of these overlaps between those parts are, it's kind of being covered up right now, but let's just select this piece and we'll go in here. I believe it's maybe with this one. We look at the bonded contact there. This is the one that I'm kind of concerned about. There's really no, we're not going to have a weld there. They did overlap just a little, but that's really not a contact that we want to use. We're going to suppress that one. And then same thing on the other side. Those are not going to be bonded contacts because it's only welded to the piece in the middle. Okay. Same thing on this side. Let's open up that clamp. So again, this is just kind of verifying everything in your model. Let's see. Grab this one. That's a good one. That one's a good one. This is the one we want to suppress. And then this one will suppress too. So, not that that would have maybe changed the results a whole lot by having those bonded, but we want to make sure it's going to react like it should in real life. So, all right, I think my contacts now are set up properly. We've got our forces applied. We've got the fixed constraint up on top. So let's just go ahead and move forward with the mesh and see what we get here. So we'll go mesh. So I went through, you can see the size. These elements are pretty large, so depending on the size of the part, it changes the mesh element size. So if we need to refine that at all, we can sure do that. But just for a first stab, I usually just try the default initially, but we can definitely go in and change our mesh settings in order to get maybe more accurate results. All right, let's try once we have our mesh created, we run the simulation. Let's go run here. Saying it's separated, the sauce ring, that's normal, was added. And I guess one thing we didn't really do was kind of try to determine where we thought, well, we did it maybe a little bit. Where do we think the highest stress would be within this thing? And we can see that, up on the top, we've got the high, fairly high stress right where those welds are. So, whether we need to change, a piece up there, or maybe instead of having a weld, maybe bolt on that top piece could potentially change. We've got a little bit of, obviously you can see the deflection. This is obviously exaggerated. It's not going to deflect that much unless you're, really over the top. But if we look at our overall stress, let's see, we got 10.99 max. We'd want to compare that. That's megapascals. We'd want to compare that with the, the yield strength of the material that we're using. Actually, I should have. I did not verify the material either. I guess I know it was applied here. So we want to go back in and very up on top assign the material, and just to make sure everything was applied correctly, and each of these had the right material. So definitely something I should have shown earlier, but we can do that here by selecting the assigned material. So that pulls up and it shows that the generic material was applied to this, which we didn't care. We took that out. Those pieces were all taken out, but it looks like the other pieces, steel mild. We've got some stainless in there, potentially for the hardware pieces. So it looks like the material was applied for everything else, which is good. So just to kind of go back, mesh, simulate, run again, now that we know that our materials are correct. And again, you can kind of go through and see you've got some stress obviously in those angles. We kind of expected that. But if we look at some of these other pieces, where are we seeing any higher stress throughout those joints? So I don't see a whole lot. There's a little bit right in there, but overall those arms seem to be strong enough if that's what we were concerned about. But again, up on top, if we verify that our stress is highest there, and if we make a change to that, maybe the high stress is going to move to a different component, and then maybe we'd still have to be concerned about that. So we want to make sure it converges if we make any changes, and optimize the design after doing a couple of these. So, all right, well, I think that kind of wraps up what I wanted to show today. Hopefully you got a little bit of insight on how you can utilize Inventor Professional and the simulation environment within that to go through an analysis project. Obviously there might be some more iterations required here, but again, some of the key things to take away are what type of analysis can be performed, and the other sessions coming up, they'll probably discuss this a little bit more in depth on when it makes sense to use one of the other tools. But this is a nice comparison chart. If you go out to, this is on Autodesk site, so their website, autodesk.com, products, Nastran, InCAD comparison. You can just Google it too and try to just do Inventor Professional versus Nastran, InCAD, or Simulation Mechanical. But it goes through and shows what the capabilities are here, kind of a check mark next to each of them that, so Inventor Professional can do a lot of the stuff these other tools can do, down until you get to, the heat transfer, linear or nonlinear. Some of these linear structural, like buckling and stuff like that, we can't really do within Inventor Professional. And then obviously you get into the nonlinear and the multi-physics, then you have to kind of bump up to one of these higher level tools. Okay, but definitely a lot of stuff, a lot of capabilities within Inventor Pro. So hopefully you're able to learn something today, and look forward to seeing you at our next webcast. So thanks, and have a good day.